Thanks, John. So I'm here today, and I'm to be here. I'm going to talk to you about my passion. So I've been obsessed with space since I was very little. I think a lot of us can identify with that. When I was young, in my bedroom, I had Earthrise as a mural on my wall. So Earthrise is that famous photograph of the Earth from the moon. So suffice to say, I wanted to be on the moon. I still want to be on the moon, but now I'm going to help, at least try to help astronauts get there. So in college, that passion continued. I studied orbits and trajectories, and that's what I'm going to talk to you about today. So I learned how things move in space, how to get from point A to point B. And what's interesting about that is, I think now that I know that, a lot of the things I see in movies just, get it wrong all the time, right? And so one of my favorite lines, it's not a space movie, but one of my favorite lines is from Back to the Future, where Doc Brown says, "Roads, where we're going, we don't need roads." And he's talking about flying car, not space. But we kind of conflate the two sometimes. We think about it the same way. We think, well, okay, I want to go from this planet to that planet. I'll just go on a straight line. But it doesn't really work that way. There's something called gravity that gets in the way. And so, on Earth, we don't really worry too much about gravity. I mean, it's important for us. We, can stand on the surface, but it doesn't vary very much. I mean, we're only a few miles above the surface, and so the 1G is almost extremely constant. So even in the airplanes, I mean, we take off, we land, but it doesn't make a big difference. In space, it makes every piece of difference. And so I'm going to show a little video here to give you a kind of a glimpse of how to think about gravity in this context. This is called a gravity well. And what you're seeing here is the force of gravity as it pertains to your distance away from the planet Earth. And so what you see here is really the fact that it's inversely proportional to the distance squared. The force is, and the energy is inversely proportional just to the radius. And what you see, that means that the force of gravity is very strong when you're close to the Earth. So what we need to do is we need big rockets that propel us off the surface of the Earth. It's a big part of what we need to do to get into orbit. And we need speed, because if we just, say we're far out in one of these places, if we don't have any orbital speed, the force of gravity will just pull us right into Earth and we'll just crash right into it. This is kind of maybe basic for a lot of you guys, but the idea here is we have to use a lot of force to just get off the planet. Now, on top of that, once you're in orbit, there's all kinds of different orbits to think about, and one of the ones we talk a lot about is LEO. We're familiar with LEO because that's where the space station is. It's one of the lowest orbits you can be in. And one thing to kind of think about is LEO is actually pretty far down the gravity well. So this arc here at the bottom of this picture shows just how low energy that is. That means if we want to get to the moon, we need a ton more energy to get there. And so that's something I've been thinking about. We need to figure out how to maximize the use of that energy. But it's not just about energy. We also have to know where we're going. That's a big part of it. I think we all probably know this too. And so we have to figure out, if we have the orbital velocity, we still need to match where we're going to the moon. So the moon is going to come up here in a second. We can propel ourselves out from the Earth, but if we're just targeting any old space and energy level of the moon, we're not going to get there. We have to match its orbital velocity. So that's what's going to show here. As we get to the moon, you can take any old path, but we have to actually predict where the moon is going to be, and that's kind of the fun part for us trajectory guys to design. And once we get to the moon, we have its gravity well to contend with. Now, it's much smaller. You can see, it's a kind of a dip in this video to deal with, but it also has a gravity well, and it's energy we have to dissipate to land on the surface of the moon. So in this gravity well, there's also something called low lunar orbit. This is the orbit that Apollo used when it went to the surface, but it's pretty low in the gravity well as well. And frankly, we have to decide if where we're going to rendezvous, where we're going to do things. Apollo landed, rendezvoused its lander in LLO, but is that where we want to do for future missions? This is something we have to think about. We have to decide, how we want to do these energy trades. And so, what kind of orbits are out there? Well, there's a myriad of orbits. We can do any size of elliptical orbits. Elliptical orbits are the most useful for getting transfer in deep space because we want to use the Oberth effect to slingshot our way out. But there's all these choices. I mean, not only are they planar, like these 2D ones you see here in the Earth and Moon, there's 3D ones, different planes and different things. Say we want to go to the South Pole of the Moon, which we've been asked to do. What kind of orbits do we want to be in now? So I want to talk to you a little bit about not just two-body orbits, but multi-body orbits. This has really been the most fascinating thing I've been able to look at. There's something called a halo orbit. So I'm going to show in this video is different families of these orbits, and they exist because of the play between the Earth and Moon gravities. So what you see here is a halo orbit in plane around L2, and as we expand the family, you can see how it approaches the Moon. So there's we can choose any one of these orbits if we want to put something in orbit, and these family actually extends to the moon, which is in that center there. And there's something called a near rectilinear halo orbit. So that's a mouthful, but what it means is we actually have these orbits that pass close to the moon. You may have also heard of something called a distant retrograde orbit. That's what this family represents. They're planar, very stable orbits, and that's why they're appealing, because they have the stability characteristic. But they also exist because of the Earth-Moon gravities. Here we see the juxtaposition of these more polar-looking near rectilinear halo orbits on top of the DROs. And here are the different families. So there's basically an almost infinite number of orbits we can explore. So the question remains, how do we get to the moon? Do we stop in one of these other orbits? Do we go to LLO? And here, this is where it comes down to the rocket equation, one of the most fundamental things we think about. So the NRHO energy on this video shows it's much higher. It's out of the gravity well. Is that a good thing? Is that something we want to use? It just depends on the architecture. So let's think, I'm going to pause here in a second on a picture of a bunch of heavy lift launch vehicles. And let's think about the rocket equation. The rocket equation tells us that if you have a certain energy change, a certain velocity change, and you have a certain efficiency of your engine, well, then you need to know, how much mass you're moving, and that will tell you how much fuel you need. So you have all these different kinds of launch vehicles you might want to use, and you have to just ask yourself, well, what's the most efficient way to move? And kind of one of rocket science's 101 is let's stage our rocket. And so what does that mean? That means that you don't want to, until we have a force field that can cover our propellant, which would be great, please invent that, but we have tanks, and these tanks are heavy. And so, like the Saturn V here, it had 4 stages just to get to the moon. Why? Well, you don't want to carry all that dead weight around. And so that dead weight just is an anchor to your rocket. So you drop off that dead weight and you move on. And that's the efficiency of staging. Now, you might ask yourself, well, I've heard some things about this thing called a BFR or a Starship. I mean, isn't that a single stage? And why are they doing that? Well, actually, it's kind of a multi-stage, because what they actually do is they refuel that tank in orbit. So basically, you're taking advantage of the reuse, the refueling. You're basically staging. So basically, in everything we want to do, we want to maximize that staging. So then you have to ask yourself, well, okay, depending on the launch vehicle we have, what do we want to do the delta V? Do you want to do the delta V on the crew capsule or the lander? For the moon, we think there's basically 2 major things you need. You need a crew reentry capsule and a lander. So you got to decide, what things you're going to put the delta V on. And so the question becomes, we need to think about what we have. And so for the systems we have, like Orion and SLS, if we start with those, and we think about what we want to do with those, we have to think, do we want to add delta V to the Orion? Do we want to add delta V to the lander? How do we want to move? And what it comes down to is, the Block 1 SLS example in Orion has the ability to get into this NRHO that I was talking about. And the question is, do we want to add more delta V to that, get down to low lunar orbit, or do we want to add that delta V to a lander and rendezvous higher? And it's not necessarily a simple choice, one or the other. We got to ask ourselves, what's the efficiencies of these different vehicles? And the Orion has a heat shield. It has parachutes. It has a lifetime of 21 crew days. It has all these features that make you think, okay, well, do I really want to move that around a lot? Do we want to take that down into the gravity well? And maybe we have a lander that's lighter. Maybe we have a lander, maybe similar to the Apollo LEM, that is less weight than the Orion capsule. Then maybe we want to take that instead from the gateway orbit down into the gravity well. So that's a question we have to ask ourselves. And one more thing before I let you go here. There's some really cool trajectories that you can get to the NRHO. This video shows something called the Ballistic lunar transfer. I can't claim that I found these myself, but I have great engineers and academics who have discovered this. What you can do is if you go on a translunar injection to the moon, instead of doing a big burn to get into orbit, you can take your time over months, use the gravity of the moon to capture into orbit. So what you're seeing here is literally almost a free insertion into orbit. And so if we have time, which we would if we have a lander that doesn't have any crew systems on it, maybe doesn't have cryopropellants that might boil off or evaporate, then we can take advantage of that. So in other words, there are lots of places to rendezvous. We can do LEO rendezvous, we could do high elliptical Earth rendezvous, we could do LLO rendezvous. But we have to ask ourselves, what do we have available to us today? What do we want to use for the future? And how do we make this sustainable architecture work? And so that's why we proposed the Gateway orbit to do this. This near rectilinear halo orbit. And this video shows a little bit how that might work in terms of a phasing. So this green arc is going to show Orion coming out, and you're going to rendezvous with the Gateway in orbit. So stop there. We do this powered flyby, insertion into orbit. Now we're in this big 6.5 day orbit. We're going to coast for a little while, and then we can do our transfer down to the surface, these quick transfers. Stay on the surface for one rev of the orbit, and then come right back. So what we see here is one concept for how we would do a mission to the lunar surface. I, for one, am extremely excited about the return to the moon. It's not only important for our own national goals, it's important for our international cooperation, and it's important for our missions to Mars. So thank you very much for listening, and have a good day.